And then, yeah, the others, please, as people join, just pay attention. And Timo,
Good luck.
you can. Are you already online?
Yeah.
Yeah. Okay. Uh, yeah. Maybe then we can already start. So, hello everyone, and welcome to our seminar series on non-Hermitian physics. Before we start today, I just want to remind you about our house rules to make sure that the talk goes smooth. So we ask everyone to keep the microphone and the camera switched off. After the talk, we will have a Q&A session where you will be allowed to ask your questions. And during the Q&A session, you can either use the raise hand function of Zoom, or you can also type your question in the chat, and then we will allow you to unmute and ask your question to the speaker. We also want you to know that this talk is being streamed and recorded on YouTube. After we are done, it will be available for everyone there. If you are on YouTube and you have any questions, you can just type it on the chat and we will pass it to the speaker. So before I introduce you the speaker of today, I want to tell you that on the 22nd of November, we will be receiving Dr. Benjamin Stickler from University of Ulm. So this will be the next talk in the series. And today it is my pleasure to introduce you to Professor Peter Murch. I have like a short bio here for him. So he got his PhD at the University of California in Berkeley, where he worked on the group of Professor Dan Stamper-Kurn. Then he went for a postdoctoral research period, also at the University of California, in the group of Professor Irfan Siddiq. And then since 2014, he joined the Department of Physics at the Washington University in St. Louis. Kater, thank you very much to be here with us. You can share your screen now, and the stage is yours.
Excellent. Can you hear me and see everything okay?
Yes.
All right. Just have to drag my Zoom bar out of the way. Great. Well, it's my pleasure to join you all here. It's a beautiful morning here in St. Louis, Missouri. And I know it's getting to be the afternoon there in Europe. So my talk is about the interplay of energy dynamics, memory, and thermodynamics, experiments in non-Hermitian and open quantum system physics that we perform here at Washington University in my experimental lab. So let's go ahead and get started. And I want to start the talk with a
Sorry, Kater, you were muted.
Okay, great.
Yeah.
Thank you.
Yeah.
We'll start with a I tried to change the slide and I muted myself. I'm very competent. Okay, so this is a story, passage about a conversation Feynman was having with his father. And his father says, so Feynman, I understand that they say light is emitted from an atom when it goes from one state to another, from an excited state to a state of lower energy. And Feynman says, well, yeah, that's right. And so Feynman's father asks, so if the photon comes out of the atom when it goes from an excited state to a lower state, the photon must have been in the atom in the excited state. Feynman says, well, not really. And so his father continues, well, how do you look at it so that you can think of a particle photon coming out of it without having been in there in the excited state? And eventually Feynman becomes frustrated. He says, look, I don't know. I can't explain it to you. It's complicated. So Feynman was famously adept at explaining physics to other physicists who already knew what he was talking about, but maybe not the best at explaining physics to non-experts. But all this is to say, Feynman and his father were talking about spontaneous emission. And that's the process by which an atom emits a photon and thereby shedding light on the world around us. And it turns out that spontaneous emission is ultimately responsible for the vast majority of the visible light around us. Here I am staring at my computer screen. It's powered by light emitting diodes, and the light comes out of those light emitting diodes because of spontaneous emission. Right, and it turns out that this is kind of fun, that the spontaneous emission is actually responsible from the visible light that we see from the sun. And I know what you're thinking. You're thinking, well, actually the light from the sun comes from this nuclear fusion in the core, but actually that creates very high energy gamma ray photons that slowly work their way to the surface of the sun. And the visible light that we see is actually from spontaneous emission from the plasma on the surface. That is, at a quantum level, we have Bremsstrahlung radiations related to free electron transitions. So you have different electron states, and you have transitions between those, giving rise to emitted light. And you could ask, okay, what is that spontaneous emission or stimulated emission? And this brings us to Einstein, where his A and B coefficients tell us about the ratio of spontaneous emission versus stimulated emission. That is, stimulated emission is enhanced by the photon density of states. And so we can assume the sun to be, say, a thermal black body source at 6,000 Kelvin. We can find that the ratio of spontaneous emitted light versus stimulated emitted light is about a factor of 400 for light in the green or yellow wavelengths, and 300 in the red wavelengths. So to the extent that the sun can be treated as a black body, most of the visible output is due to spontaneous emission. And the reason I told this little story about spontaneous emission is because it gets at some of the core ideas that we'll harness in our experiments to study non-Hermitian dynamics. And that starts with the idea that we think about light as photons. And that's because most of the time when we detect light, we detect it with detectors that are sensitive to individual quantas. Think about a photomultiplier tube, a charge coupled device, our eyes. In our eyes, a photon is absorbed by some molecule, creating some cascade of electrical excitations in a nervous system. And so in most cases, we think about detecting light in a quantized form. And the idea is that the way that we detect the light conveys a certain story about the atom that emitted the light. That is, if we think about here a schematics of two atomic levels, and the particle represents the system being in the excited state, and the device here is a photon detector, we can tell the story of spontaneous emission in the following way. At time t equals 0, the atom is in the excited state. As time progresses, the detector is silent, waiting for a photon to be emitted. And at some point, the photon detector gives a click, indicating that a photon has been emitted by the atom, telling us that there's been a quantum jump from the excited state to the ground state, and so on. Now the atom is in the ground state, and the story of this spontaneous emission event has been told. The point is that there's a very strong relationship between the signal that we've received, the click at some point in time, and the state of the atom. That is, it made a quantum jump from one state to another at a specific time. But it turns out that light has both a particle and a wave nature. And so what is the story of spontaneous emission when we detect the wave nature of light rather than the particle nature of light? And that was a question I first set out to explore experimentally in my lab back when I was first setting it up here at Washington University nearly a decade ago. Question was, what if we measure the emitted light from a radiatively decaying atom using a homodyne detector? That is, a homodyne detector detects the wave nature of light. It asks, does the emitted light interfere constructively or destructively with some local oscillator, some phase reference? And so we constructed a system where we could monitor the spontaneous emission of an atom, but detect that light not with photon detectors, but with homodyne detectors to measure the wave nature of light. And so when we constructed this apparatus and we turned on the detector, we saw the following signal. You can see a trace here of the voltage we collected on our homodyne demodulation device. versus time, and it's a bunch of noise. And indeed, this is what we expect. This is the quantum noise associated with the electromagnetic vacuum, or maybe more precisely, the electromagnetic vacuum with one photon of energy deposited in it over some time scale of roughly 1 microsecond. So we're measuring one quadrature of the electromagnetic field, and indeed, because the vacuum state is a Gaussian distribution, in those two quadratures, we're just seeing those quantum fluctuations. So now that our signal is very different, it's not just a silent detector that gives a click at a certain time. What is the new correspondence between this signal and the state of our atom? Well, to solve that, we had to open up some textbooks on quantum measurement theory. And it turns out that one can decompose this noisy signal that we've detected into a series of measurement events, which we can associate with a series of measurement operators. And so starting with some initial state of the system, we can apply those measurement operators corresponding to each measurement results to construct a piecewise continuous trajectory for the state of this atom, maybe described by a density operator rho, or more conveniently, we could express it, since it's a spin half system, in terms of its Pauli expectation values, sigma x, sigma y, sigma z. And the essence of the physics behind this is that the emitted light corresponds to an interaction A dagger sigma minus. The atom is lowering a state, we're getting one photon in the field. And the homodynamic detector measures a quadrature, something like A plus A dagger, which is then related to the real part of sigma minus, or the sigma x Pauli operator of the qubit. The emitted light tells us about the sigma x component of the qubit as a function of time. But of course, that information is masked by the quantum fluctuations, which puts us in the realm of weak measurement. Okay, so here I want to show you what we infer for the quantum dynamics of this spontaneously emitting atom as a function of time as we record this measurement record. So each measurement record tells us information about the state. And so when I apply the theory of quantum measurement to this, I infer a quantum trajectory for the state that doesn't just jump abruptly from the excited state, which is placed here at the top of this plane of the Bloch sphere. It diffuses slowly down through the Bloch sphere, making its way to the ground state, which is at the bottom over a certain time scale. Now, I should mention, if we had perfect measurement efficiency, there was no additional noise contaminating our signal, these trajectories would be confined to the surface of the Bloch sphere, finally making their way to the bottom, to the ground state. And of course, each time we perform this experiment, we get a different set of noise and therefore different quantum trajectories for the state as they diffuse from the excited state to the ground state. Okay. So in the past 10 minutes or so, I've alluded to two different unravelings of the master equation, as we call them. So in the case where we're detecting photons emitted by atoms, we infer quantum dynamics associated with quantum jumps. That is, different iterations of the experiment, we detect photonic clicks at different times, and we find the atom jumps from the excited state to the ground state abruptly with a quantum jump. Now, if I were to average over hundreds or thousands of these runs of experiment, I would recover the familiar exponential decay that's expected from spontaneous emission. Okay, but if we detect the wave nature of light, we instead infer different quantum dynamics for the state of this atom that we call quantum diffusion. We have trajectories that sort of diffuse their way toward the ground state. Sometimes they go faster to the ground state. Sometimes they move away from the ground state. They become more excited during the emission process, but eventually they find their way to the ground state. And fortunately, if I average many of these quantum diffusion trajectories together, I recover the exact same exponential decay that I have for quantum jumps. So in that way, these are two different unravelings of the master equation, two different ways to interpret the quantum dynamics based on how we detect the environment into which it's emitting photons. Okay, so that master equation I'm referring to is the Lindblad master equation, written here, which describes how the density operator evolves in time. And there's a component having to do with some unitary evolution. And then there's two terms that correspond to the dissipative interaction with the environment. One of these is called the jump term, so term associated with these quantum jumps I've described. and the other is called a coherent non-unitary term. Now, when we talk about tracking specific quantum trajectories, what we've added to this master equation is an update associated with information we determined from the signal. Okay, so we can turn this into a stochastic master equation which tracks the individual dynamics of a single quantum trajectory. Okay, but now that I have this Lindblad master equation introduced to you all, I'll show you something quite intriguing about this master equation, which we started to figure out maybe after working with it for several years in our lab. And it's the following. If I somehow eliminate the jump term from this master equation, okay, just imagine we can do that in some manner, what I'm left with is a piece of the master equation, which I can actually write as an effective Hamiltonian. This Hamiltonian is the generator of time translation, yet it's expressly non-Hermitian. So it's a non-Hermitian Hamiltonian. So by eliminating quantum jumps from this sort of dissipative interaction, we can generate non-Hermitian Hamiltonians. And this is something we're after exploring. And of course, the idea is that when you have a non-Hermitian Hamiltonian, among many other things, one has complex energies, and these complex energies give rise to interesting and new dynamics. Okay, so this is all based in experiments that we do. And the way that we do these experiments is in an experimental architecture we call superconducting transmon qubits, or superconducting cavity quantum electrodynamics, or superconducting circuit quantum electrodynamics. There's many different names. At its simplest rendition, the atom that we're studying is a transmon qubit, and it's formed by a Josephson junction shunted by a capacitor. So there's two energy scales in this system, EJ and EC, and a transmon works in a regime where the Josephson energy, EJ, is much greater than the charging energy, EC. In the end, a reasonable coordinate to think about is the phase associated with the inductance of the junction. That's this phase phi. The Josephson energy dominates, and so we have a potential that's roughly the cosine potential. And so we have a potential energy landscape that's a cosine, and there are certain bound states of this finite potential. Well, ground state, an excited state, another excited state. There may be 5 or 6 excited states in total. These are just as good as atomic energy levels, except for that I can pattern them with circuits and I can apply other tricks to them. So these are our artificial atoms that we choose to work with. And of course, they're fabricated devices. So the devices are made from depositing aluminum on silicon and sort of nanometer size scale features, embedding that on that chip inside a microwave cavity to realize the physics of cavity quantum electrodynamics. Okay, and so in order to realize this effective non-Hermitian qubit, we take this cavity, we close it up, and we couple that to a shaped density of states. We've tuned something about the environment in such a way that we can engineer a hierarchy of decay rates between these multiple atomic levels in this artificial atom. And so in the end, we have arranged a situation where the excited state decays to the ground state relatively quickly, 8 times per microsecond, but the F state decays relatively slower compared to that. And so in order to study non-Hermitian dynamics, we need to remove quantum jumps from the dynamics of this dissipative qubit. And we do that in the following way. What we'll do is we'll initialize the system in this F state, that's the second excited state, and we'll allow it to evolve into some effective Hamiltonian. So here I've drawn some arrow J, which indicate there's some unitary coupling between the two, some drive that couples the excited state and the F state. All the while, there's a potential for the excited state to decay to the ground state. We'll let that dynamics take place over the course of several microseconds, if we like. And later on, we'll post-select in the qubit manifold. That is, we'll disregard any trajectory where the system has undergone a quantum jump to the ground state. And we do that by performing a single-shot, high-fidelity readout of the state. So we might, in that readout, find that the qubit is in the artificial atoms in the excited state, which is fine. It might be in the F state, that's also fine. But if it's decayed to the ground state, a quantum jump has occurred and the qubit is no longer existing because our qubit is these upper two states. And so we throw that data away and try the experiment again. So we're able to realize this no-jump evolution through post-selection. Great. Great, so let me give you just a little intuition about what this post-selection does and what can be interesting and exciting about the associated non-Hermitian dynamics. So what I'm showing you is non-Hermitian Rabi oscillations. So to remind you, normal Rabi oscillations is the case where I just have a two-level system and I drive a coupling between the two states. And so one expects the probability that it's in the initial state evolves as they say the cosine of some Rabi frequency t. And so we just see oscillations at a specific Rabi frequency in time. But now we're looking at Rabi oscillations in the context of this non-Hermitian Hamiltonian. And so instead of looking like a nice cosine oscillation, we have oscillations that are highly distorted. That is, the oscillations are very slow to go from the F state to the excited state, and then very fast to oscillate back to the F state. And this can be seen in the context of the measurement back action from the post-selection. That is, because the excited state has a high probability of decaying at any given point in time, it's relatively unlikely that if the qubit is still around at the end of the experimental protocol, that the qubit was in the excited state, which means that the fact that we still have data, we still have a qubit to study, favors that it's in the F state. So we have dynamics that favor one state over the other. If you like, the F state has gain relative to the excited state's loss. So this way, the measurement back action favors one state over the other. And in that way, the non-Hermitian dynamics can be associated with this type of post-selection measurement back action. Okay, so let's get a little bit more specific about the system. We're interested in this upper manifold of states, the excited state and the F state, and we're coupling with a Hamiltonian term J sigma x, which is a drive we apply with a detuning delta from this transition. And so when I study just the evolution of this qubit, I have the following effective non-Hermitian Hamiltonian, that is delta minus I gamma over 2, J on the diagonals coupling these two states. Okay, so that's a non-Hermitian Hamiltonian, but given the Hamiltonian, I can go ahead and calculate the eigenvalues and eigenvectors that any quantum mechanics student would do as a first step in understanding a certain system. So here's the eigenvalues of this Hamiltonian, and the somewhat nasty looking complex number. That is, the eigenenergies of the system are, of course, complex, and we can express then the eigenvalues in terms of the eigen vectors in terms of the eigenvalues. So I'll plot you in more detail the eigenvalues of this system here as a function of the two parameters which we can readily tune in the system. So those two parameters are J, that's the strength of the coupling between the two states, and delta, the detuning between the two states. And here's the imaginary parts of the eigenvalues, and here's the real parts of the eigenvalues. Now, the eigenvalues are complex in general, and so they form these Riemann manifolds, which tell us what the energy landscape of the system looks like. And because the eigenvalues can be complex, these Riemann manifolds have interesting topologies and connections and branch cuts and degeneracies that are going to be critical to what's interesting about non-Hermitian dynamics. Okay, so first I'll draw your attention to a degeneracy in the system where both the real part and the imaginary part of the eigenvalues coalesce. And this is what we call an exceptional point degeneracy. That is, it's different than a conventional degeneracy of a Hermitian Hamiltonian that is a diabolic point, in that an exceptional point degeneracy has both the eigenvalues and eigenvectors becoming degenerate. Now, perhaps the most compelling thing one can study when one has this Riemann manifold energy landscape to play with is the physics of dynamical encircling. So here's a sketch of our parameter space again. There's two parameters we can tune, delta and J. And the idea is to start in an eigenstate of the Hamiltonian for some initial value of delta and J, shown here with the dot, and then slowly to adiabatically tune the parameters such as to encircle this exceptional point, coming back to the same place where we started. Why is that interesting? Well, if I look at the shape of this Riemann manifold, if I start in one energy eigenstate of the system and slowly encircle the eigenstate, I'll pass around through this branch cut and end up on the lower Riemann sheet after one full tuning of these parameters. That is, I've taken the qubit from one state to the other by slowly adiabatically tuning these parameters, and that way I've gone from one state to another using the topology, the way that these energy landscapes are connected. Now, there's more to this because there's also an imaginary part to the energy eigenvalues. And so we'll have to be careful to study how some paths follow paths where the imaginary energy eigenvalue is relatively small and negative, or the imaginary energy eigenvalue is large and negative, corresponding to significant loss. And so there'll be some asymmetry in this, the physics of encircling, due to the fact that some paths pass through regions of significant loss, while others don't. Okay, so in order to study this, we're going to use quantum state tomography. So we'll prepare a certain state, and what we can do, because this evolution is really taking place in real time in the lab, is we can tune just a fraction of the way around, pause the measurement, pause the system, make a projective measurement of the qubit in any basis that we like to reconstruct what is the quantum state at each point in time. That way we can get a sense of exactly how the state is evolving as we perform this parameter sweep encircling this exceptional point degeneracy. Okay, so here's that experimental data that we took. What I'm plotting for you is the expectation value of the three Pauli operators, sigma x, sigma y, sigma z, respectively in blue, red, and black. Those are the solid lines. And as a guide to the eye, I've plotted also the dashed lines are the instantaneous eigenstates of the Hamiltonian as for each variety of these parameters, as delta and j vary. And so for the most part, you can see that we start off in one eigenstate of the system, eigenstate where the expectation value of sigma x is nearly -1. And at the end of the parameter sweep, we end up in the other eigenstate where the expectation value of sigma x is approximately +1. Now, it's not perfect. There are other non-idealities. In particular, you can see these wiggles here come from the fact that the evolution is not perfectly adiabatic. As the real part of the eigenvalues get very small, approaching this branch cut, the change in the Hamiltonian is too fast to be truly adiabatic. That leads to some coupling between the two eigenstates. And so we see oscillations of the characteristic energy gap of the system here at the end of the sweep. There are some other non-idealities, but for the most part, we see what's expected given the structure of the energy eigenstates of this system. Okay, so in pictorial representation, we've started off in one eigenstate of the system, called psi minus. There's some non-adiabatic coupling and quantum jumps that leave us in that same state, that break the sort of ideal picture of this Riemann manifold. But for the most part, when we make a counterclockwise sweep around the exceptional point, we transfer population from one state to the other. Now, if we do the same experiment, but tune the parameters not in a counterclockwise direction, but in a clockwise direction, we see something somewhat different. That is, we can see that after some period of time, the system becomes very noisy. And that's simply the fact that we're passing through a region of large negative energy eigenvalues, a region of significant loss. And so for the most of the experiments, the system decays from the excited state to the ground state, and we throw the data away. So the data quality is terrible, even if we average for a very long period of time. And so we don't see this state transfer effect when we perform the sweep in the clockwise direction. So there's a chiral behavior due to the fact that one path experiences loss while the other experiences relative gain. So if you like, in this second case, while we do have some transfer from psi minus to psi plus due to the topology of the Riemann manifold, the vast majority of the population is lost due to post-selection. So this sort of chiral population mapping has been studied in a vast variety of systems because it's sort of a paradigmatic feature of these non-Hermitian Hamiltonians and exceptional point degeneracy. And we're also able to see those and see the salient features of those effects with our superconducting qubit experiment. So I've mentioned two things about dynamics associated with non-Hermitian Hamiltonians. That is, we've seen these distorted Rabi oscillations. That is the effect of the non-Hermitian Hamiltonian or the post-selection, however you like to look at it, leads to distorted Rabi oscillations, where dynamics favor one state over the other. And we see things resulting from the topology of the energy landscape that is just encircling and state transfer. Okay, but do complex energies lead to new energetics? That is, when I talk about energetics, I think about things one measures in joules, maybe, things like work and heat and energies that are related to thermodynamics. So the question I want to address now is, how does one understand thermodynamics in the context of non-Hermitian Hamiltonians where energies are in principle complex? Well, the way to tackle this is to think about the fundamental relation in thermodynamics, that is du is equal to dq plus dw. Let's see how this plays out in the context of quantum mechanics. So du, the change in the internal energy of some system, can be written as the change in the trace of rho times the Hamiltonian, which has two components to it. One is the trace of rho th, and the other is the trace of h d rho. Well, it's natural to associate this first term, rho dh, with work. That is, changing the Hamiltonian is changing an external parameter of the system. That is exactly what we define as, or think of as, work in thermodynamics. So clearly this first term corresponds to the work term. So therefore the second term must have to do with heat. So then heat has to do with changes in the energy that don't come from changes in the Hamiltonian, but have to do with changes in the state. So that's a statement of this first law of thermodynamics in the context of quantum states. And so how do these quantities, dw and dq, work and heat, relate to non-Hermitian evolution when this Hamiltonian we have is non-Hermitian? Okay, well, in order to get there, let me pause and explain how one even talks about energy changes in quantum systems. That is, in quantum systems, we can have situations where our quantum device exists in a superposition of energy eigenstates. Another final state is a superposition of energy eigenstates. How does one then talk about definite energy changes between these non-definite energy states? Well, the solution to that problem is the idea of studying energy changes in terms of transitions between definite energy states. And that's the basis of this two-point measurement protocol. That is, we're going to look at the distribution of total energy changes from transition probabilities. So we can start the system at some time in one of the energy eigenstates, say n equals 0, n equals 1, we let it evolve. And at the end, we make a measurement again in the energy basis. And so we can look at transitions from n equals 0 to final state m equals 1 corresponds to a positive work being done on the system. Other transitions correspond to negative work done on the system. And transitions that preserve the energy correspond to no work. So we instead can characterize work experimentally by looking at these transition probabilities between energy eigenstates. Great. Now, in order to make consistent thermodynamic sense of non-Hermitian dynamics, what I want to do is take our effective non-Hermitian Hamiltonian and decompose that into a couple relevant pieces. So the first thing we notice is we can pull off an overall factor of minus I gamma over 4 times the identity, leaving us with a piece of the Hamiltonian that is PT symmetric for delta equals to 0. This piece here, this overall loss term, really reflects that we have a post-selection probability that's decreasing exponentially in time. And so when we post-select on the no-jump evolution, we're really realizing the physics of this latter part of the Hamiltonian. Okay, and then I can further write this Hamiltonian as a sum of both a Hermitian piece and an anti-Hermitian piece. And our understanding, or the way that we will consistently define thermodynamics, is to allow dynamics to be dictated by the overall Hamiltonian, that is the sum of the Hermitian and the anti-Hermitian part, yet the energetics, that is the basis by which we'll make this two-point energy measurement to define changes in energy of the system, will be based solely on the Hermitian part of the Hamiltonian. Okay, and so our goal is to demonstrate the validity of the second law of thermodynamics, which is given by this Jarzynski equality, which is a equality statement of the second law of thermodynamics, and it says that the exponentiated work, the average over the distribution of that quantity, is equal to the exponentiated change in free energy of the system. Okay, so that's our goal. So this takes us to our experimental protocol. So again, we have these three energy states. We need to prepare our qubit in this excited set of states here. Then we'll allow the system to evolve according to some time varying Hamiltonian. And then at a later time, we'll make a high fidelity single shot readout to post select on the EF manifold to select away the quantum jumps. And we'll use these measurements to determine these transition probabilities, that is, from the initial eigenstates to the final eigenstates of the Hermitian Hamiltonian. And from that, we can determine the work distribution, which has three possible values, 0, +1, then -1 in respective units. From that work distribution and the probability of initial states given initial thermal temperature of this qubit, we can determine this work distribution averaged over an ensemble of trajectories. So this is the quantity that goes into calculating the Jarzynski equality. The important idea is that while we tune these parameters, we can make sweeps that encounter different areas in the energy landscape of this effective non-Hermitian Hamiltonian. That is, regions where the eigenvalues are purely real, where the eigenvalues are purely imaginary, where the eigenvalues are complex. And so to make our lives simple, what we'll do is study just a few different types of trajectories in this energy landscape. One is where we maintain a value of delta equals 0, and we simply tune J to a smaller value and then back to its initial value. And another parameter sweep where we take J constant and we change the detuning to some positive value back to its initial value, or some negative value back to its initial value. We're focusing on parameter sweeps that preserve the same initial and final state, simply because that keeps the initial Hamiltonian and the final Hamiltonian the same, meaning that the change in free energy will be equal to 0. So the Jarzynski equality simply states that the average exponentiated work distribution should be equal to 1. Okay, so we set about studying this experiment for a course of several years, studying all the possible ways in which we could do this incorrectly. And now I'll show you the results of all that hard work, which is the average exponentiated work versus time for different types of parameter sweeps. So the first case we consider is the case where we park the qubit Hamiltonian to be static Hamiltonian, where we initialize eigenstates, we let it evolve under the non-Hermitian Hamiltonian for some variable period of time. Then we measure the transition probability to determine the average exponentiated work. And what we see is within the sort of typical experimental noise that the average exponentiated work is equal to 1. So that means that if we have a static Hamiltonian, even if it's a non-Hermitian Hamiltonian, that the Jarzynski equality is preserved. Okay, now the next experiment we do is we've taken the state, and over the course of a variable period of time, with a period ranging from, say, 0.2 microseconds to 1 microsecond, we've tuned J to a smaller value and back. And again, we see that the Jarzynski equality is valid, even as we're dynamically tuning the Hamiltonian while maintaining the system in the so-called PT symmetric regime where the eigenvalues are purely real. Okay, next we'll take the value of J and we'll tune it past the exceptional point, entering a regime, the so-called PT symmetry unbroken regime, where the energy eigenvalues are purely imaginary. We find even in this case, the Jarzynski equality is still valid. Yet finally, now for sweeps, we're changing the detuning for static J, say on a negative path or positive path. Now we see significant deviations for 1. That is, the Jarzynski equality is no longer valid for dynamics where the Hamiltonian has a non-zero detuning. So what's going on is this detuning is breaking the pure antilinear symmetry of this PT symmetric Hamiltonian. And that's ultimately resulting in a breakdown in our thermodynamical definitions of heat and work. Okay, so what's going on here? Well, this 2-point energy measurement that we discussed measures the change in energy of the system, total change in energy. The Jarzynski equality is valid if given our measurements of the total change in energy, if those are equal to the work, because the Jarzynski equality has to do with work applied to the system. Okay, so the first law tells us that, of course, the change in internal energy can have a work component and a heat component. And since I know the evolution of this system is governed by the Lindblad master equation, I can work out exactly how the state changes in time, given this quantum dynamics. And so I have this differential equation here. Now, the first thing to note is this first term here, corresponding to the unitary evolution, contributes nothing to this expectation value due to the cyclic property of the trace. So I'm just left with the second two terms. One of those, the piece having to do with quantum jumps, is often referred to as classical heat. This is what we think of as heat, is that the system is jumping between energy states as it exchanges energy with the environment. This other term, which corresponds to the non-Hermitian evolution, has the term of quantum heat, which I'll explain more in the following slides. Okay, so what is the difference between classical and quantum heat? Interlude. So first example is, say we have a qubit, which I've initialized in the ground state with the Bloch vector pointing to the ground state. And I apply a pi/2 rotation to this qubit state, putting in a state along, say, the x-axis of the Bloch sphere. And then I make a measurement of this qubit in the z basis. Well, I can have one measurement outcome that takes the system to higher energy, and one measurement outcome that takes the system to lower energy. Okay, so where does this change in energy come from? Well, it comes from the preparation impulse. That is, we've applied work to the system to put energy into it that we then reveal when we make a measurement of the system. So that's an example of work. Second example, let's say I have a qubit that is initialized in a thermal state at inverse temperature beta. I make a measurement of this qubit in the z basis, and I find that sometimes it ends up in the excited state, and more often than not, it ends up in the ground state. So where do these energy changes come from? Well, they come from the reservoir, they come from heat, they come from the fact that we're in a thermal state. Okay, final example. Let's say I have a qubit in the ground state, and now I make a measurement, but not in the z basis, but rather in the x basis. Well, in this basis, I can make a measurement, one measurement outcome is along plus x, and that other measurement outcome is like minus x. Both of these measurement outcomes correspond to a higher energy of the qubit in its energy basis. So where does this energy come from? Well, this is the essence of quantum heat. So it comes from the fact that the measurement doesn't commute with the system Hamiltonian, that we have incompatible observables, and therefore there'll be energetic consequences to this measurement interaction. And this is what Alexia Offay and her group has dubbed the term quantum heat. And that comes into play in this non-Hermitian dynamics because quantum heat is associated with this effective back action from our no-jump evolution. Great. So what's going on is we have this, so now we're going back to our qubit. When we studied the evolution in the PT symmetric regime, where we saw that the Jarzynski equality was verified, we had the following pure PT symmetric Hamiltonian. This corresponds to a situation where the F state has gain, which corresponds to effective positive quantum heat flowing into the F state, whereas the excited state has relative loss, which corresponds to an equal amount of quantum heat flowing out of the excited state. The eigenstates that we consider in the PT symmetric regime are simply symmetric superpositions of the excited state and the F state, meaning that these states have equal parts heat flowing in and heat flowing out due to their equal contribution from the excited state and F state, which have equal and opposite components of heat. So in this way, the PT symmetric Hamiltonian leads to an effective thermal isolation. That is, heat is flowing into the system, heat is flowing out of the system, yet the net heat flux is zero. So in this case, the total change in energy is simply equal to the work, and therefore we have a valid Jarzynski equality when we measure the work distribution using the 2-point energy measurements. However, for the case of non-zero detuning, where now we have a delta term here, breaking the pure antilinear symmetry of this Hamiltonian, eigenstates of the Hermitian part of the Hamiltonian correspond to now unequal overlap of the E state and the F state, meaning that there's a net heat flux into one state relative to the other. And so the states are no longer thermally isolated simply by the fact that there's not the perfect cancellation of these gain and loss terms. So in this case, our 2-point energy measurement captures some of the net heat from the environment, and we don't have a valid Jarzynski equality when we measure the work distribution using the 2-point energy measurement. Okay, so let me wrap up and summarize what I've been trying to tell you. We've been talking about energy in open quantum systems. So for generic open quantum systems, we can study the evolution in terms of a Lindblad master equation given here. We can apply work on the system by changing external parameters in the environment, and we can also define energy changes due to interactions with the environment as heat and work in some consistent way. If we instead switch to the case of the no-jump evolution and effective non-Hermitian Hamiltonians, now we can describe the state using a state vector, psi, and an effective non-Hermitian Hamiltonian that's a generator of time translation. When we do this, we end up having complex energy spectra and energy exchanges with the environment that can be decomposed into quantum heat and work. When we have a perfect antilinear symmetry, that is perfect PT symmetry in the system, we have an effective thermal isolation, which means that all of the heat contributions, the heat exchanges with the environment are canceled out, leading to effective thermal isolation. Okay, that's all I wanted to say. Let me stop by acknowledging the collaborators and students, postdocs who worked on this project. This project about studying the thermodynamics of non-Hermitian Hamiltonians is the work of a student in my group, Sarah Erdemar, and we've had a long-standing collaboration with Yogesh Yogalkar and postdoc Weijian Chen in my group, and Mariam Abbasi, the PhD student who also initiated these experiments. So thank you all for your attention today, and I'll be happy to take lessons for the next 10 minutes before I have to go to my class.
Thanks, Kader, for the nice talk. We are now open for questions. So I see that Sanchar has a question. Sanchar, you can unmute yourself and ask your question.
Hello, yeah, thanks a lot for a great pedagogical talk. I was a bit wondering about the way you differentiate work from heat. So at least my classical understanding is always that heat is sort of like the high entropic energy. If you put energy into a system, you can either put it in a high entropy way or you can put it in a low entropy way. And I always thought sort of like the low entropy part is the work and high entropy part is the heat. But what you are saying here seems to be something quite different than at least my understanding. So can you explain a bit more of why the distinction? Can you explain the distinction a bit more?
Right. So in thermodynamics, I think one way to think about it is we can have a system that's isolated from the environment. We can make energy changes of that. We can do the same experiment where the system is no longer isolated from the environment. And if I do the same protocol, the difference in energy between those two different protocols, we call that heat. This is the change in energy that wasn't due to work. Work is this measurable quantity. So sure, heat has deep connections with entropy and entropy changes of the system. But I guess the idea is that the most natural definition, and this is somewhat common in thermodynamics, quantum thermodynamics, is to identify work with changes in external parameters, that is, changes in the Hamiltonians. The idea is that dW and dQ, of course, they're imperfect differentials. They depend on the path and all sorts of things like this. But this is a natural definition for heat and work for quantum dynamics, which we've shown through many different types of experiment really consistently define thermodynamics for quantum systems. But I think there's also room to try to define these in different ways and also show that we have consistent thermodynamics. But this is what I consider to be an established definition.
Yeah, of
Thanks.
course I believe. I'm just trying to understand you. So, okay, so one small question is, if the first term I can interpret as the work you do on the system, I imagine.
Sure.
Is there any component here which is sort of like the work done by the system to the environment or to the measuring apparatus, or that doesn't exist?
Very interesting point. So in the case of quantum heat, which corresponds to the coherent non-unitary evolution. Okay, maybe put it this way, if I can skip to that part of the slide. So we have these two terms, classical heat and quantum heat. Classical heat has to do with sort of quantum jumps, scrambling of the state. This is the sort of incoherent evolution, non-unitary evolution of the state associated with quantum jumps. That is a feeling of increasing the entropy of the system, what you would think of as normal heat.
Okay.
That's the reason why we call this other piece of heat, which comes from the evolution of the state, but is really associated with the kind of measurement back action, the way the measurement apparatus is changing the energy exchanges with the measurement apparatus as quantum heat, because if you like, it's somewhere in between work and classical heat in that it's coherent and unitary. And so that leads to the sort of sticky, interesting physics of non-commuting measurements and how the measurement apparatus is changing the system measurement. So I think you're getting at the core of what's interesting about quantum heat, is that it's somewhat different than classical heat.
Okay, thanks a lot.
Okay, so I saw that someone before. Okay, Clara has a question.
Thanks very much for the very interesting talk. I was wondering how scalable this is. So would you be able to couple two transmon qubits, for example, and how would this change then the post-selection process that you would need to perform? Thanks
for that question. So indeed, we can scale this to 2 qubits or even more qubits. If we have a system, and now it's a very interesting system of 2 of these non-Hermitian qubits, then we pay this post-selection price twice. And so our success rate is even lower, and the scaling of that is quite bad. Let me say there's some very interesting things that can be done. For example, if I have 2 of these non-Hermitian qubits undergoing these types of Rabi oscillations that have this big distortion, one can create interesting situations where they become faster. They become very entangled. They become entangled faster than they would normally given Hermitian evolution. So even if they're very weakly coupled, they can become very rapidly entangled. So it's interesting physics to do, but indeed the post-selection scalability is problematic. We also have plans, and we have those kinds of experimental systems in the labs. So they're readily feasible. One can also consider something like a spin chain of many Hermitian qubits coupled to one site that's non-Hermitian. And it turns out that one site, that we only do one set of post-selection, imbues the whole lattice with effective non-Hermitian dynamics and complex energies. And so one can gather this type of physics without post-selecting particularly much. So I think there's a reasonable hope of it being scalable. The final point is that this post-selection approach is only one of many ways to generate non-Hermitian Hamiltonian. We can also generate this with asymmetric hopping between lattice sites. So we have plans to study cases where we just have asymmetric coupling between different qubits. In that case, there's no post-selection at all, but we still have the same effective non-Hermitian Hamiltonian. And so that's a more scalable approach to studying larger quantum systems with non-hermiticity.
How can you get the asymmetric hopping without post-selection? I would have thought that you could, for example, get this by a non-local dissipator, but that would also require then post-selection.
Yeah, so the way to build these sort of non-reciprocal couplings in quantum systems is to introduce another mode, and so then to drive parametric reaction, coupling between modes, and you arrange things so that the phase accumulates in a certain way that one direction has constructive interference and one direction has destructive interference. And so it's a bit more complicated, but one can use basically interference effects to get asymmetric transport in these lattices.
I see. So you're keeping the third mode. So that's the point. Okay, very interesting. Thank you very
Thanks.
much.
Yeah.
Yeah, let's take a final question by Patrick Potts. Yeah.
Hi, yeah, thanks very much for the very nice talk. Can you hear me?
Yes, I can.
Yes, very good. So I have a question about the quantum heat. You had this example of a thermal state that you monitor, and then you end up in one of the energy eigenstates. Now, during this monitoring process, the system is not connected to heat baths, so there's no heat exchange with the bath, but still the conditional state would change its energy. So, but this is a completely classical process, right? You can do that in a classical system. So where would that type of energy exchange go in? Would that go into the quantum heat?
So this type of energy exchange I would associate with classical heat. And the way I think about it is the initial state is described by a density operator. So it's really just a classical mixture of ground state and excited state. We've generated that mixture of states via quantum jump type of exchanges with the environment, and the measurement simply reveals which one of those states it is in. That is, this measurement, because it commutes with the density operator, is non-evasive. It's not changing its measure energy in any way. So it's just revealing what state it was in.
But in
so the measurement doesn't change the energy in this case. It just reveals which one of those states it was in.
Right, but in your, I mean, when you wrote classical heat and quantum heat beneath the terms of your master equation,
right?
Wouldn't it be exactly those terms where you labeled quantum heat that would actually get you to one of the eigenstates and in this conditional evolution? Because there's no jumps going on.
I think the way to think about this, so the state that we have of the qubit thermalized with the environment is realized by evolution with the environment, characterized by this master equation, in which case we have a state that's thermalized to a certain state, and I think one needs this jump term in order to realize that state. That evolution of the thermalization doesn't involve a post-selection on quantum jumps. When we make a measurement, now we're taking that outside of this evolution. That's just a projective measurement to the energy basis, or if we like, we can add a stochastic update term, and those terms are really revealing what state it's in. So I don't think one associates quantum heat with that measurement process. So when the measurement commutes with the system's Hamiltonian. If you like, there's a great description of this in these papers by Cyril Hilard from Alexia Alfay's group. So they study this process in quite detail in these theory papers.
Okay, thanks a lot.
Okay, Kader, thanks very much again for your talk and for the interesting discussions. Just to remind everyone, the next seminar series will be on the 22nd of November with Benjamin Stickler, and hope to see you all soon. So thanks.
Excellent. Thank you all. Have a great day.